Today my topic is damped harmonic oscillator. For this experiment we need a spring mass system and immersed in a this mass immersed in a oil bath. Whenever we stretch this spring in the downward direction, then the body gets oscillated in the y-axis. So here, due to spring mass system, the body oscillates like this, but due to this oil, this body stops after certain time. That means the oscillations are converted into damped oscillation. Damped oscillation means the decreasing amplitude. So at a certain time, it will be stopped. So we have to find the damped constant and the forced constant also. Then we have to equate this force constant and damp constant. Then we have to check three cases. For this expression, we have to take a second order differential equation. That is first step. Next one is we have to assume a general solution of that equation. Then by differentiating that general solution, we have to substitute again in the second order differential equation. Then after that we have to find roots of a quadratic equations. So these are the three processes involved in this expression. So let us consider a mass m suspended from spring and set to vibrate. This spring set to vibrate, it is observed that the mass vibrates for a long time in air compared to the mass which vibrated partially in liquid kept below the mass. So if only spring mass system, this body vibrates more time, but due to immersion of this oil, the vibrations are in the decreased manner. Now after stretching of this spring, a restoring force is proportional to the displacement but oppositely directed. Suppose a spring mass system is stretched like this by using force. Then after releasing this force, this body moves in the upward direction. Actually we stretched in the downward direction, then it moves in the upward direction, which is opposite to the force. Now F is proportional to minus x here. For this is we applied force in the downward direction. The displacement is x in the upward direction. Then the restoring force Fr is equal to minus mu into x. Here mu is force constant. That means force constant or proportional constant or material constant. That means the metal also you have to consider. The frictional force is proportional to the velocity by in opposite direction. Whenever this body immerses in the downward direction, the oil objects the velocity of the body. So the velocity also decreases. The velocity can be expressed, that means the force, the frictional force F is always minus dx by dt, proportional to minus dx by dt. Dx means change in displacement by unit time. This is dx by dt means. Now ff is equal to minus r into dx by dt. That means the frictional force is equal to, where r is called frictional force constant. That means this frictional force depends upon the nature of the oil. That means the liquid whatever we used in the beaker. Then but the force according to Newton's second law, we know the F is equal to mass into displacement m into a. That means this can be written as mass is constant. The acceleration can be written as d square x by dt square. This is change in velocity by time. Now we have to make a final general equation. That means the total force is equal to the total force is equals to the restoring force plus frictional force. Actually this force, this restoring force also opposite to this force, and the frictional force also opposite to this force. Again I have written this equation, F is equal to Fr plus Ff. Now substitute the corresponding values of these terms. F is equal to m into d square x by dt square is equal to restoring force minus mu into x, frictional force minus r into dx by dt. Now divide m both sides, then mu x by m both sides, and r by m into dx by dt. Then take these terms into left hand side, then we get the positive values. That means dx square by dt square plus r by m into dx by dt plus mu by m into x is equal to 0. Now we have to replace at the position of r by m. I have to put 2b here, and at mu by m we substituted omega square here, where b is called damping constant and mu is called spring constant or force constant. This is taken as equation number 1. So this equation number 1 represents a second order differential equation. This second order differential equation can be solved with a general solution. That means we cannot solve this equation directly. Then let its solution be x is equal to a into e power alpha t. That means the solution in terms of an exponent value here. Then a means a and alpha are constants here. Now differentiate this equation, then we take as x here. We have to substitute this equation in equation number 1 here. Now x is available here to substitute, but we need dx by dt and d square x by dt square. That means we have to differentiate this equation once with respect to time. This is dx by dt is equal to, differentiate this value, a is constant, alpha into e power alpha t. This is equation 2a. Then again I have to differentiate d square x by dt square, then that is equal to a alpha square into e power alpha t. This equations, this is x value, this is dx by dt value in terms of exponent, and d square x by dt square in terms of exponent value. Now I had to substitute this equation 2, 2a and 3, this 3 in equation 1 here. Now substitute equations 2, 2a and 3 in equation 1. I have substituted a into alpha square into e power alpha t, then 2b into a alpha e power alpha t, and omega square into e power a into e power alpha t. Now we have to consider, we have to take a common factor of a e power alpha t here. Then this equation becomes like this. Then but a into e power alpha t will not be equals to 0. There is no possibility of this term equals to 0, but there is a possibility alpha square plus 2b alpha plus omega square is equals to 0. This is a balanced equation. We have to find the roots of the above equation. This, according to roots of quadratic equation, we know very well alpha is equal to minus b plus or minus b square minus 4ac by 2a. From this equation, this is like ax square plus bx plus c, like that, this equation. Now at the position of a, this is a equals to 1, then b position, that is 2b, and c equals to omega square. Now substitute these values in this equation. We get minus b plus or minus root of 4b square minus 4 omega square by 2. Now take 2 as a common factor, then 2 gets cancelled. Then alpha is equal to minus b plus or minus root of b square minus omega square. Here we got two roots. One is real root, another one is imaginary root. Then let alpha 1 is equal to minus b plus root over b square minus omega square. It is a real root. Then alpha 2 is equal to minus b minus root of b square minus omega square is an imaginary root. By using these roots, two roots, the general equation will be x is equal to, there are two roots are there, that's why I split it into two types here. This is a1 into e power alpha 1 into t, this is a2 into e power alpha 2 into t. Then we have to substitute values of alpha 1 and alpha 2 here. Then the final equation will be, the general equation will be x is equal to a power minus b plus root of b square minus omega square into t. Another one is a2 into e power minus b minus root of b square minus omega square into t. This is equation number 4, where a1 and a2 are arbitrary constants. This is the general equation of this concept. Now we have to study the cases here. Then the b represents damping constant, omega square represents the spring constant or certain frequency. Then for case 1, for overdamping damped motion, when b square is greater than omega square, that means the damping is more than that of the driving oscillation. So when damping is more, then the oscillation decreases very quickly. As we know, in this case, the body once displaced, it returns to its equilibrium position quite slowly without performing any oscillation. Whenever we stretch spring once, then without any oscillation, then it goes to its equilibrium position very slowly without any oscillation. This type of motion is called overdamping. That means without oscillations, it goes to its equilibrium position. For example, the needle in the moving coil galvanometer. In moving coil galvanometer, the needle will be like this. Then if we apply any power, then it goes to like this. It goes to its position, that's all, without any oscillation. Second one is critical damping. In critical damping, when the condition is when the damping constant is equals to spring constant, then both are equal, then again I have taken this general equation, x is equal to a1 e power minus b into plus root of b square minus omega square into t, then a2 into e power minus b minus root over b square minus omega square into t. This is from equation 4. Now I have taken this power value b square minus omega square. Here b square is equal to omega square, then this becomes 0. If b is equals to omega, then it will become 0. But here in this expression, which is not equals to 0, it returns very small value. It returns some very little bit of value, that is h. Now I have to substitute this h in this equation. Then x is equal to a1 into e power of instead of b square minus root over b square minus omega square, we have to substitute h here, minus b plus h into t plus a2 into e power minus b minus h into t. Now then we have to take e power minus bt as common factor. Then the displacement x is equal to e power minus bt into a1 e power ht plus a2 power minus ht. Then hence in this case, the particle tends to acquire its position of equilibrium much rapid than case 1. Such motion is called critical damped motion. The example is voltmeter and ammeter. Suppose the needle is like this, voltmeter. Whenever we switch on this meter by applying some voltage, then the needle goes like this, and it stops one position, at a position. So after 2 or 3 oscillations, it gets this equilibrium condition, and ammeter also like that. The needle moves like this. Then suppose this is stopped position, it moves like this. Then it comes to its equilibrium position. Then it shows the reading. In third case, underdamping. That means the damping is very much less than that of the spring constant. So again we have to take the equation root over b square minus omega square. Here when b square is less than omega square, when damping constant is very much less than spring constant or driving constant, then this equation becomes minus of b square minus omega square. Here minus means which represent minus 1. Minus 1 is nothing but minus 1 root over minus 1 is nothing but I. This is complex value I into b square minus omega square. Then b square minus omega square is again I have taken in the form of beta here. Now the amplitude of motion is continuously owing the factor e power minus bt, which is called damping factor here. That means whenever the damping factor is very less, then this body oscillates like this without any stopping. That means after certain oscillations only it comes to equilibrium position. Okay, the example of this concept, that means underdamping concept, is motion of simple pendulum in air. That means this is possible when we remove the beaker with oil. If we remove the beaker, then it oscillates freely. Another thing is the moving coil of ballistic galvanometer. Moving coil of ballistic galvanometer also like that. The needle moves like this, then it comes to certain position. Another thing is electric oscillations of LCR circuit. These are the examples of this underdamping condition. This is the diagram for underdamping. At initial position, the amplitude is maximum like this. After certain time period, the amplitude slowly decreases like this. This y-axis represents the amplitude and t represents time. If we draw a graph between displacement and time, we will be getting a damping oscillator diagram. At a certain after certain time, this will be equals to 0. This question is very important for B.Sc students. Now R19 batch first B.Tech students also. Okay, prepare well. Thank you.